Okay, so strong titrations, here we go. This goes quickly. But along the way, there's a couple other things that we need to talk about. So let me quit this, let me clean this up. And guys, be judicious in terms of the notes that you take. But today, guys, we're going to talk about strong titrations if you want a topic for your notes. So guys, where would be a good place for you to pick up? You know what, probably, I don't think you need to write anything down on this first page. Tell me if you agree. But guys, as we get into this idea of titrating, guys, what you're going to find out, and again, you don't need to know this list, but it provides structure. Guys, there's actually 4 types of titrations that you need to be aware of. And they go like this. So strong titration, strong acid into base or strong base into strong acid. Then guys, we've got weak strong or strong weak. So we've got a weak acid being titrated by a strong base or a weak base being titrated by a strong acid. That's what we're going to do next time. Then guys, we have polyprotic titrations. That means that we've got an acid or a base that can give away more than one hydrogen or more than one hydroxide. Guys, they actually just wrote this out of the curriculum. We're not going to do it. There may be like one, maybe. Remember when we talked about polyprotic acids and we said the first hydrogen comes off easier than the second? That's all you need to know. And then guys, finally this, weak titrations. So you've got a weak electrolyte being titrated with a weak electrolyte. You will not see this until your junior year in college. Okay, because this involves calculus, because it's like a related rates problem. You've got 2 related things going on simultaneously. Are you doing cardboard too? Okay, thank you. So guys, this then becomes our tasks. So this is what we're going to do today. This is what we're going to do next time. Notice that I didn't include, thank you. Notice that I didn't include titrating buffers on here because we've already done it. So looking forward, this is today, this is next time, these are gone. So guys, when we talk about titrations, you okay with this idea that we're just adding one thing to another in a controlled manner? That makes sense, right? Okay, so guys, what we can do then, and this is what we did in lab last time, these are the graphs, and you know, I should give these graphs. Jeanette, let me give you a copy of these. These are actually the graphs these are ours. These are the graphs that we created last time in lab. So guys, these are the graphs that we talked about. And so when we track these labs, what we do is we track the pH of the mixture as we add the strong acid or the strong base to it. Now guys, this is a thing that we talked about in second period, but let's make sure we're clear. Guys, when we draw these graphs, what's equal at the equivalence point? The moles, right? The amount of acid that we've added to the base or the amount of base that we've added to the acid are equal. And guys, it's at that moment that the indicator changes color, right? Go ahead. Yeah, so let me show you. So the idea is this, and this may bring this back for you. If you remember what we did last year, Jeanette, in this virtual chem lab space, I'm going to do this super fast. So the idea is this, going into the titration bench. So we run in here, let's grab some HCl, let's grab some NaOH, let's go back into the lab, let's pull these into the lab. Let's grab a beaker, throw this on here. We'll put sodium hydroxide in the burette. We'll put HCl in here and then in here, and then we'll stir this. And so what we can do then is we can add base to the acid, and as we do, the base is neutralizing the acid, right? Right, and that's why I didn't do that. I'm so glad you said that. But guys, the chemistry that's taking place then is this. The NaOH, which is in the burette, is reacting with the HCl that's in the beaker. And the products of this are NaCl and water. But as you guys all, and it's neat that you thought of that, guys, in order to know when we have added just enough base to neutralize the acid, we need something to tell us when this thing hits pH 7. And the something that we use is an indicator. And the indicator that we use is actually phenylphthalein. And so we grab this and we add the phenylphthalein. And now as we add the acid to the base, and guys, I'm just going to do this really sloppily, but as we add, the base to the acid, at some magic moment, I went way past it. But at some magic moment, this turns pink. And guys, the reason that this turns pink is it's telling us that this thing reached pH 7. And at pH 7, the only stuff that exists in the beaker is this. Salt, sodium chloride salt in water, and that has a pH of 7. So when we reach pH 7, the only stuff in the beaker is this. If the only stuff in the beaker is this, that tells us that we added exactly enough of that to neutralize all of this, meaning that these numbers of moles are equal, and that's the equivalence point. Is that coming back to you? Is that okay, Jeanette? So that's the whole idea with the equivalent. That's a really, really... What if you have a polyprotic acid? And we used to have to talk about that, and now we don't. All of our acids will be monoacidic and all of our bases will be monobasic, so we don't need to worry about it. Frankly, it's not that big a deal because especially, like, what if our acid was sulfuric acid? Then the only thing that changes is when we do the dimensional analysis to figure out how many moles of acid we have, it's just a 1-to-2 ratio because this will actually give away all of its protons in the presence of the strong base. And so it changes that, but we don't need to worry about it anymore. Is that okay? Okay. So guys, with all of that said then, it brings us back to here. And so guys, as we're generating this information, what we do is we use these indicators to indicate when we have stoichiometrically equal amounts of acid as base or base as acid. And then we track these things using titration curves, which again is pH versus volume of titrant. And we saw those in second period. And then Jeanette, you have those curves in front of you, and we're about to throw them up on the screen. So guys, just sort of a 30,000 foot view of titration. You guys okay? Okay. So guys, the first thing then that... And guys, you don't need to write any of this down, but they will ask you these questions in multiple choice on the test. So you need to understand at some superficial level how indicators work. And guys, the thing that you need to understand is this. Most indicators, guys, are actually just weak acids. So, guys, phenylphthalein is actually a weak acid. And because phenylphthalein is the one that you're most familiar with, it's the one that I want to show you. So, guys, this is actually how phenylphthalein works. Don't write any of this down, but this is the idea. So guys, this is a phenylphthalein molecule. This is actually what it looks like. So this is phenylphthalein. It's a big old organic acid. And guys, this dude right here is actually the acidic acid in the phenylphthalein molecule. Now, what happens with this is this phenylphthalein molecule actually reaches equilibrium with its conjugate base. So guys, that is the conjugate base of phenylphthalein. Now, the other product, of course, is protons because we remove that hydrogen from the phenylphthalein and we end up with the conjugate base and then the hydrogen that gets released. Now, guys, this is the magic that makes this thing an indicator. what happens is this. It turns out that the phenylphthalein molecule in water is colorless. You want to guess what color its conjugate base is? It's pink. So here's the way that this works. So when I hand you that dropper of phenylphthalein, it actually contains this system at equilibrium. It's dissolved in alcohol rather than water, but it contains this system at equilibrium. Now guys, here's the trick. If you take this system and if you put it in an acid, so something with a pH lower than 6, if you put this in a system that is acidic, that means that that system, when we put this into the acid, there will be, it's acidic, there's a lot of hydrogen. Guys, what direction does that drive the equilibrium? You get it? It's colorless. So guys, this indicator is colorless in environments that are acidic because it's the conjugate base that is colored, and an increase in hydrogen forces the equilibrium to the left towards the colorless side. Well guys, what happens if we put this in a base? Well, if we put this in a base, what does that do to protons? Grabs a hold of them, right? These dudes react together and they form water. So what does that do to the concentration of protons? It goes down, the equilibrium shifts to the right, and it turns pink. Guys, that's the way that all indicators work. The thing that you need to understand, though, is that not all indicators make this switch at pH 7. And disturbingly, it turns out that phenylphthalein doesn't make this switch at pH 7. Did any of you notice that when you did the graphs last time? Guys, if you were watching closely and if you were watching your titration as it was stirring, when that thing turned pink, it wasn't at pH 7. It turns out that you'll understand why in a minute that was okay. But guys, phenylphthalein does not turn pink at pH 7. What determines this is a hard question. Think about this. What determines the pH at which it does turn colors? That's actually on the AP test. Guys, what is it that determines the pH at which any of these indicators will change color? It has to do with that relationship, the relationship between the conjugate base and the conjugate acid. But how do we describe mathematically that relationship? Ka. See guys, these are weak acids. They have Ka values. You don't have to do the math, but you can actually figure out the pH at which any of these indicators will change color by knowing the Ka value of the dissociation of that weak acid. You don't need to go there, but you do need to understand that the color at which they change is a function of P or of Ka. So do you guys get the idea here? Fundamentally, what you need to know is that indicators are weak acids that have conjugate bases that have a different color. And therefore that makes them sensitive to pH. Is that okay? Okay. All right. So guys, with all of that said then, let's now talk about these titration curves. And Jeanette, you have this in front of you. So guys, this is a titration curve. You've seen these before. You generated them in lab. Jeanette, you have them in front of you there. But so guys, contextually, this is exactly the same titrations we did in lab, or Jeanette, the one that we just did in the virtual chem lab. What we've got here, and guys, I would encourage you to scratch this into your notes. If you just do this, because we need to tear this apart a little bit. If you do this, let me switch colors. If you do this and draw an X and Y axis, if you put milliliters of sodium hydroxide here, if you put pH there, and then scratch a curve, noticing, guys, that that curve looks exactly like the graphs you guys generated. It's actually pretty cool to me when things that we do in lab are supported by the things that we're learning in class. And this one supports very, very well. But guys, now's the time to finally label these graphs. So have you scratched in what I've got you? Would it be easier if I just scratched my own rather than use this? Or are we okay? Okay, so guys, as we're looking at this curve, these are the things that we need to be able to think through. First of all, I think you understand, but just to make sure, the idea here is that our sodium hydroxide is our titrant, and then our acid is the thing that we are titrating. Now guys, what about this curve tells us that that's true? There's several things, but what tells us that's true? Good. It goes from low pH to high pH, which means we're starting with an acid, neutralizing it, and then continuing to add base. The other one, it kind of tells us right here. Guys, on the x-axis, your units will always be the volume of your titrant. Then guys, the next thing that you need to be aware of with these curves is we think of these curves as having 4 sections. We have initial. I need to recalibrate my board, guys, but I'm not going to. That should be a circle. We have initial, we have before equivalence, we have at equivalence, and we have past equivalence. So those are the 4 regions in this graph that we're going to talk about. And guys, what you've got to be able to do is calculate the pH in each of those regions. So guys, let's talk about it. When we talk about, oh hey, there we go, small circles are better. So guys, when we talk about calculating the initial pH, what does that math look like? Just the negative log of what? The molarity of the acid, right? So guys, in this case, this is a strong acid. So let's say HCl plus NaOH. So guys, this is a strong acid. Because it's a strong acid, it completely dissociates. Consequently, to find out the pH is just the negative log of the molarity of whatever the acid is. So if you want to write that in, you could just go pH is equal to the oh boy. So guys, pH is then equal to the negative log of whatever the ion is, whatever the molarity of whatever the strong acid is. So guys, let's pick the other easy fruit. Of these 4 regions, the other region that's relatively easy to figure out the pH for is this one. That's just 7. And again, the chemistry is at equivalence. Guys, at equivalence, all we have is products. By definition, we've added just enough base to react with all the acid. Those are equal. Because those are equal, these are gone. The only thing we have left is products. Sodium and chloride are both non-reactive towards water. They're negligible. And consequently, we basically just have water and its pH is 7. Yeah. That's different. That's Thursday. Because on Thursday, we're going to talk about weak acid titrations, and then this math is pretty complicated. You'll be fine with it, but this is where the math gets complicated, because this won't be at pH 7, right? Because the conjugate base ion will attack the water, and we'll talk on Thursday. Okay, yeah?
I just have a quick question.
Mm-hmm.
So, about the pH, so when it's, is this the thing where like the molarities are the same?
No, so I think what you're referring to is the idea that when we build buffers, if the molarity of the weak electrolyte and the conjugate base salt, if those molarities are the same, then pH is equal to pKa. That's a different thing. Yeah, yeah. You guys okay with those 2 ideas? Okay, so now guys, this. Remember, again, this is important. The chemistry that we're talking about is strong base into strong acid. There is no equilibrium here. Strong base into strong acid. The acid is in the beaker, the base is in the burette, strong base into strong acid. So guys, when we're doing that kind of chemistry, what are the units that we need to do the calculations? Moles or molarity? Moles, right? Because it's not equilibrium. So guys, the question then becomes this. How do we figure out the pH here? And how do we figure out the pH here? And guys, this is interesting. The answer is subtraction. Here's the way this goes. When we are before equivalence, that means that think about this. When we're before equivalence, it means that we have not added enough base to neutralize the acid. Let me say that again. When we're before equivalence, we have not added enough base to neutralize the acid. So what then determines the pH? And the answer is this. The amount of hydrochloric acid that has not yet been neutralized is responsible for the pH. Does that make sense? Let's say that again. So before equivalence, we have not neutralized all the acid. So the pH is determined by the amount of HCl that has not yet been neutralized. So how do we figure out how much HCl hasn't been neutralized? Guys, the answer is this. Figure out how many moles of this we start with, subtract from that how many moles of that we've added, and the difference between the two is the unneutralized HCl. Convert that into a molarity and take the negative log, and that gives us the pH. Is that okay? So guys, what about up here then? Well, up here it's the opposite, because when we're past equivalence, all the HCl is gone, and now it's just like dumping sodium hydroxide into water. So in order to figure out the pH of this, we still need to know the number of moles of each. Then we subtract, and the number of moles of NaOH minus the number of moles of HCl tells us the extra NaOH that we've added, and that will then let us figure out pH. Do you kind of understand the theory? I think you'll understand it better when we put it into practice. So guys, there's one more thing that we need to talk about, and then we're going to do some math and call it a day. And guys, it goes like this. These are what are called endpoints, and this is a term you need to know. Guys, when we do titrations, we're looking for the indicator to change color. We call that point the end point. It's the end of the titration. When the color changes, you are done. That's the end of the titration. So we call that the end point. But guys, here's the thing that's interesting. The end point for phenylphthalein is actually pH 8. Guys, phenylphthalein turns pink at pH 8. But where is the equivalence point for a strong acid-base titration? 7. So guys, we've got a problem. We've been using phenylphthalein to find the equivalence point. Think about this. Because remember, when we titrate, like when we do HCl plus NaOH, we stop titrating when we've added just enough base to consume all the acid. That's the equivalence point. So we've been using phenylphthalein to tell us when this reaction is over. But this reaction is over at pH 7, and phenylphthalein doesn't change color until pH 8. So guys, does that mean that all of our math has been based on incorrect data? And the answer is no. Why is it appropriate to use phenylphthalein, which changes color at pH 8, to find equivalence at pH 7? Why does that work? Go ahead, Susanna. Yeah, and it's actually not basically the same. It is the same. The idea is this, guys, if you can picture it. You are adding, am I in drawing mode? You are adding sodium hydroxide drop by drop by drop by drop by drop. And then, guys, you add that one, and you saw this in lab, you added that one magic drop, and the pH functionally went from pH 3 up to pH 10.5. And that one drop that you added that caused that pink color to persist drove the pH through the equivalence point, through the end point of phenylphthalein, and all the way up to pH 11. So guys, there's no reason for us to have an indicator that changes color at pH 7 because the same drop that drove us to pH 7 also drove us through pH 8, and the color change happened on the same drop, so that's good enough. Do you get the idea? Okay, you're going to find out this doesn't work in weak acid titrations, and we'll look more at that on Thursday. Yeah. Yeah, because what happens is this, that first, and maybe did you, I don't know if you tried this, did you add that first drop that caused it to turn pink and then wait for any period of time? Because what you'll actually find is if you allow that thing to continue to stir, eventually the pink goes away. Didn't one of you actually show that to me? Was that you guys? There you go. And that's the problem, is that one drop of pink, actually, it's weird. It drives you up to here and then it sort of retreats. It's that additional drop that does that. And that's the drop that we want to measure the volume of. You guys okay? Okay. So guys, all we need to do now is figure out what this math looks like. And it goes like this. So guys, these are, don't write this down, strong titrations, no equilibrium. Therefore, guys, these calculations are going to be done in moles, right? So guys, we're going to do some then of these calculations. And so it goes like this. Guys, if you want to write this down with me, you can. But we're going to do the math. It says this. Calculate the pH when the following quantities of 0.1 molar sodium hydroxide have been added to 50 milliliters of 0.1 molar hydrochloric acid. So, because I love to draw pictures, we got a beaker, we've got a burette. In the burette, we've got 0.011 molar, 0.100 molar sodium hydroxide. Down here, we have 50 milliliters of 0.1 molar HCl. You guys ready to go? Do you understand the question? Okay. So guys, question number 1 goes like this. Calculate the pH when the following quantities of sodium hydroxide, our titrant, has been added to the acid. So question number 1 is this. 0 milliliters of NaOH. What's the pH? 1. Do you see it? Guys, the molarity of the acid is 0.1, right? If we have not added any base to the acid, how do we find the pH of a 0.1 molar HCl solution? Take the negative log of 0.1, right? Because the entire sample of HCl breaks into protons and chlorides. That's what makes it a strong acid. And so consequently, the pH, before we add any base, the pH is just the negative log of 0.1, and that would be 1. You guys good on that? Okay. So now, guys, what about this? Oh, man. I may have to erase because I want to... Yep. All right. I should have just asked without doing that. I don't know why this is fun to me. But it is. Okay. So now, guys, question 2. 49 milliliters. So this is the question. When we've added 49 milliliters of base to the acid, what will the pH be? Let me ask you a question first. Which side of equivalence will we be on? Will we be below equivalence or above equivalence? How do you know? Yeah, because it's less base than acid, but that logic only works when the molarities are the same. But they are, so they are. So guys, let me show you an easier way to solve this problem. So what does the pH depend upon? And the answer is the pH of this depends upon the amount of HCl that has not been consumed. Does that make sense? We have got 50 milliliters of HCl, 49 milliliters of equal molar sodium hydroxide. So we're going to have some HCl that hasn't been consumed yet. That will determine the pH of the solution. But remember, this is an equilibrium, so it has to be in moles. So guys, this is the easiest way to solve these problems. Will there be more moles of acid or will there be more moles of base? Acid, because there's greater volume and their molarities are the same. Guys, if you do this backwards, it doesn't matter, but it's actually easier if you start by looking at the one that you have more moles of. So do this with me. We have 50 milliliters of HCl. 1,000 milliliters is 1 liter. 1 liter is 0.100 moles of HCl. So we do the math. So 50 divided by 1,000 times 0.1. I get 0.00500 moles of HCl. Now guys, how many moles of NaOH have we added? Same math, different numbers. 49.00 moles, milliliters of NaOH. 1,000 milliliters is 1 liter. 1 liter, 0.100 moles of NaOH is equal to 0.00490 moles of NaOH. So guys, here then is the question. What did these 0.0049 moles of NaOH do to these 0.005 moles of HCl? Killed most of them. How much didn't they kill? The difference, 0.00, one more zero, right? 0.100 moles. Is that right? 0.005, 0.0049 minus. So 3 zeros, 100. You're right, but that's, okay, we're good. Okay, so guys, this then tells us how much HCl has not been consumed. And those moles of HCl, which are really hydrogen ions because it's a strong electrolyte, are the things that are making the pH low. So now what we need to do is figure out the pH. And pH is the negative log of hydrogen ion concentration. So why can we not just plug that number in and take the negative log of it? It's not a molarity, it's a number of moles. So Mark, this was to your original question a long time ago. How do we convert this into a molarity? Divide by the volume. But what is the volume? 99 milliliters, which is 0.099 liters. And then we go pH is equal to the negative log of oh guys, I can't even write down there. I wonder if I can go here. So here, 0.001. So guys, this is 0.00101 molar. I'm just going to do my best. So pH is the negative log. Of 0.00101. And guys, I get a pH of 3.00. Is that okay? Okay. Right here. So we started with 50 milliliters of acid. We added 49 milliliters of base. The sum of that is 49 milliliters. That's exactly right. Yep. So every sodium hydroxide that we add neutralizes an HCl. The difference is the unneutralized HCl, which is now dissolved in a larger quantity of water. Recalculate the molarity and go from there. Is that okay? So guys, with that, let me now share this with you. 49 milliliters puts us at pH 3. Because if you look, 49 milliliters puts us, again, I can't draw, puts us at about pH 3. So now the question becomes this. What if we change the game and now let's do the same calculation for 50 milliliters of base? I'm done, are you? 7. So guys, how would you represent that on the test? My advice to you would be don't do math. But it is critical that you mention that the fact that it's 7 is because the molarities are the same. So you should mention something that equal volumes of equal molar acids and bases, strong acids and bases, the equivalence point will be 7. Now, what about this? 50.5 milliliters. How will the math be different? Now we're past equivalence. We have added more equal molarity base as we have acid. How will the math be different? If we were solving this from scratch, how would it look different? Well, guys, first of all, I would switch these because now we have more base than acid. So because I know that eventually I'm going to be subtracting, I would do the sodium hydroxide first and the HCl second so that the subtraction lines up. But then, guys, after that, the only difference is the volumes. And given those new volumes, we'll now do a new subtraction, and we'll end up with a new amount of moles down here, but what will it be moles of? Sodium hydroxide. And this is where this gets different, because this will then give you an excess of sodium hydroxide, which you will then divide by the new volume, which will be what? 0.105, because it would be the sum of this and this. But guys, when you do that, that will give you a molarity, which will allow you to calculate what? Not pH, POH. And then you can calculate pH from that because pH plus POH is 14. Is that okay? Okay. So guys, you're going to have ample time to practice on these. This then is your homework, like so.